Product detailing in sheet metal. In this video, we are going to see about product detailing in sheet metal. When design of sheet metal stampings, the first consideration is shape of external perimeter. The sheet metal stampings are to be manufactured with dedicated dies. To allow satisfactory shearing in cutoff or part-off operations, the end profiles should meet the straight edges at angles no less than 50 degrees. Critical dimensions in the design of a sheet metal blank. If it is not possible, then avoid narrow weak sections in either punches or die plates. To avoidance of weak tool sections, apply to internal punched holes. That is, small holes or narrow cutouts that require fragile punches should be avoided. In addition, internal punched holes should be separated from each other. The outside edge with sufficient clearance to avoid distortion of narrow sections of workpiece material during punching. The feature dimensions and feature spacings should be at least twice the material thickness. Radii equal to at least twice the gauge thickness will minimize the corner stress concentrations in the die plate, which may lead to crack formation and failure. When formed features are being considered, the principal design constraint is the maximum tensile strain the material can withstand. This is usually called the material ductility. Typical ductility values depends on operation. Lanced and formed bridge. Thus, if a lanced and formed bridge, as shown in figure, the ratio of L to H can be calculated as follows. Assume that the transition or ramp from the surface to the top of the bridge is 45 degrees. The length along the bridge from end to end can easily be calculated as bridge length is equal to L plus 0.82 H. Assuming uniform stretching of the bridge, the tensile strain along the bridge is thus E is equal to 0.82 H by L. Thus, if the maximum permissible strain in tension is 0.22, is greater than 3.7 H, the length of the bridges should be greater than 4 times their height. A common example of a lanced and formed feature in sheet metal parts is the lower. Lowers are often formed as groups of parallel slots in the sides of sheet metal enclosures for air circulation and cooling purposes. This would not cause material failure, since the front edge of the lower would be pulled backward as the tensile stress develops in the surface. Formed hole flange. The consideration here and the choice of radius are in figure is more one of appearance and the amount of space taken up by a single lower. Another type of feature which involves stretching along a sheared edge is the hole flange. Figure shows a sectional view of this feature type. The hole flange is formed by pressing a taper-nosed punch of diameter D into a smaller punched hole of diameter D. The tensile strain around the top edge of the formed flange is thus E is equal to capital D minus small d by capital D, and this value must be less than the permissible material ductility. The limit of the ratio capital D by small d due to limited ductility limits the amount of material displaced and in turn the height of all flanges that can be produced. Typical values of flange height in sheet steel components for example, range between 2 and 3 times the material gauge thickness. In the design of beds or ribs used to stiffen open surfaces of sheet metal parts, the cross-sectional geometry as shown is important. In any case, for a required height, capital H, the width and shape of the rib must be chosen so that the required amount of stretching across the rib does not exceed the material ductility. The radius at the base of the rib must also be greater than a certain value to prevent overstraining the material on the underside of the part. This may result from the bending effect along the sides of the rib and will be considered next. When the maximum tensile strain in bending is in the outer fibers of the sheet on the outside of the bend. It is governed by the ratio of inside bend radius, small r, to sheet gauge thickness, small h. For a bend through any angle theta, the length of the outer surface is Ls is equal to small r plus h into theta. And the length of the surface in the center of the sheet on which lies the neutral axis of bending is Lo is equal to r plus h by 2 into theta. Twice the sheet thickness or greater than the inside bend radius must need punched slots adjacent to bend. For the part shown in figure, the slots would almost certainly have to be punched after the bending operation. The punching operations needed two separated dies. The manufacture of small flat sheet metal parts can be performed with a high degree of precision. Blanked parts or punched holes with maximum dimensions up to 10 cm can be held to tolerances of approximately plus or minus 0.05 mm. If we need to increase part size, then precision is more difficult to control, and for a part with dimensions as large as 50 cm, permissible tolerances are in the range of plus or minus 0.5 mm. Finally, an important consideration in the design of any sheet metal part should be minimization of manufactured scrap. This is accomplished by designing part profiles so that they can be nested together as closely as possible on the strip or sheet. Also, if individual dies are to be used, then the part should be designed, if possible, for cut-off or part-off operations. Figure illustrates the type of design changes that should always be considered. Product detailing for plastics for ease of assembly. In this video, we are going to see about product detailing for plastics for ease of assembly. Product detailing for plastics for ease of assembly. The major advantages of injection molding are easily manufactured the plastic part for ease of assembly. Effective self-securing techniques. The self-securing refers to ability to achieve a secure assembly without the use of separate fasteners or a separated bonding agent. Metal parts press fitting and riveting in this method are also used self-securing techniques. In press fitting, much larger interferences are possible compared to metal parts. This has the advantage of requiring a less precise tolerance control for the press fit. A third self-securing method, which is unique to plastic parts, is the use of welding. In this method, two or more molded plastic parts are joined by generations of intermolecular frictional heat at the assembly interface. Ultrasonic welding equipment simply had a special fixture to hold and clamp the parts. It passes high-frequency vibration of approximately 20 kHz. The detailed design of the butting or overlapping joints is critical for successful joining of the parts. Ultrasonic welding is a good economic choice where sealed joining is required. Since the equipment is relatively inexpensive and the process is fast, welding is accomplished typically in about 2 seconds. It is no exaggeration to claim that the establishment of high-integrity snap-fit designs has revolutionized the manufacturability of wide ranges of high-volume consumer products. These can be separated in two main types. The first type of annular snap-fit was developed for mating parts with circular cross-section and involves the use of an undercut and mating lip. The male partner for the mating pair may be molded with a parting plane along its axis with very little added cost, simply the cost of adding the groove feature to the cavity and core geometries. In contrast, the female or undercut part is almost always stripped off the core by the mold ejection system and is therefore inexpensively produced. The further part shapes deviate from open curves. The more difficult it becomes to eject parts from the mold, and the less robust is the assembly made.